Reentry Aerothermodynamics. Humans have been observing the sky since the dawn of our species, but early humans couldn't explain their observations. The various celestial phenomena were assigned superstition and religious meanings. Meteors were particularly noteworthy. These brilliant fireballs, when contrasted against the darkness of the night sky with electricity, were commonly thought to be heralding the descent of a higher being. We now know that these objects from beyond are pale blue dot that burn up as they attempt to enter Earth's atmosphere. This is re-entry aerothermodynamics. This presentation consists of 4 main sections: overview, the physics, examples, and the future of aerothermodynamics. Section 1, overview. Isaac Newton changed the way that humanity understood the world we live in. He discovered the laws of gravity and motion, then later invented calculus to help solve the equations he asked. His work paved the way for others later to continue expanding upon the knowledge he was able to conceptualize. Humanity wouldn't begin to be able to realize its ambitions until Robert Goddard created the world's first liquid-fueled rocket in 1926. This technology finally allowed human engineers to create things that reached speeds fast enough where the air around them would compress in a new significant manner. The previous existing equations used to explain fluid properties would no longer be applicable. Spurred on by the Cold War, humanity would begin a space race to reach beyond our planet. The space race culminated in the effort to send and return a human to the moon. One of the parts of this process would be re-entry and the aerothermodynamics involved when returning to the Earth's atmosphere. Today, we define this process as beginning at the Kármán line on Earth with differing altitudes for different celestial bodies. The atmospheric re-entry process is typically categorized into 3 stages: entry, descent, and landing, also known as EDL. EDL changes based on mission requirements and the payload. Generally, entry begins hypersonic and the spacecraft is slowed by atmospheric drag, generating enormous heat. Careful shielding is required to protect the craft from ablation, aerodynamic heating, and mechanical stress. Descent begins when the spacecraft has finished peak deceleration from body drag and deploys mechanisms such as parachutes to slow the altitude change. Landing is usually the briefest and least dangerous stage from a thermodynamic standpoint. Section 2, physics. Some of the governing equations for the space shuttle or any spacecraft in the re-entry process is gravity from spacecraft altitude, heat flow, temperature of parachute at stagnation, and the drag force of the parachute.
The goal of any design is to dissipate the kinetic energy of a spacecraft as quickly as possible while it is entering an atmosphere so that the mission objectives are not jeopardized. When an object first re-enters the atmosphere, they are usually at hypersonic speeds and have a relatively low angle tangential to the atmosphere. Spacecraft must achieve a certain optimal angle based on their trajectory to avoid bouncing off the atmosphere at low deflection or entering it too sharply and gaining too much velocity. As the atmosphere thickens and density increases, the object will stop accelerating from gravity and air resistance will decelerate it quickly towards terminal velocity. Blunt-bodied re-entry vehicles like the manned Apollo mission capsules are optimized for high drag so that they will have lower velocities and heating. This works because heating is inversely related to drag coefficient on account of the air cushioning the surface and pushing shock waves and the heated shock layer further away from the heat shield, where they dissipate eventually. Heating is the greatest threat to a re-entry vehicle because an unprotected object can quickly vaporize until there is nothing left. Metallic bodies are especially susceptible to dangerous heating because of their lower thermal resistance. For Mars re-entry, temperatures can reach 1300 degrees Celsius, and Earth re-entry is even hotter at an estimated maximum of 2900 degrees Celsius for high G deceleration. This heating comes from 2 sources: convection from collision with atmospheric gases and radiation from ionized gases and potentially debris in the upper layers of the atmosphere. These ions may also try to form reactions with the entry vehicle, so materials must be carefully chosen. A heat shield is needed to protect reentry craft payloads. The inside of a reentering object can remain near room temperature if an effective heat shield is used. Ablative heat shields, which break into small pieces to dissipate the heat they've absorbed, are used for this purpose because of the aforementioned problems with metallic compounds in reentry. Insulating composites with high thermal resistance are the best solution and may be in the form of layers of nylon phenolic in the case of Apollo vehicles, lightweight tiles filled with bonded sand like those covering the bottom of space shuttles, or wood shields used to great effect by some Chinese reentry vehicles. Descent is the stage of EDL where the space system travels through the atmosphere. Once the space system enters the atmosphere, drag will decelerate to a safe landing speed. Unpowered descent relies on body drag and parachutes more than powered descent because of this. There are 3 parachutes used to slow down most spacecraft. The first is the drogue parachute, which may activate at supersonic speeds. The pilot parachutes are used to lift and deploy the main chutes, and the main chutes are the largest and will slow the spacecraft to a landing speed. These chutes allow the safe descent of a spacecraft during the reentry process and may ultimately result in a splashdown or water landing. A powered landing utilizes rocket assistant descent motors to produce a counterforce in order to slow to safe speeds. Rad rockets are inefficient if used to completely replace parachute descent because large weights of fuel would be needed.
Section 3, Reentry Examples. The Space Shuttle is a partially reusable low Earth orbital spacecraft. The Space Shuttle uses insulating tiles on its lower surface to absorb and radiate heat while preventing conduction to the aluminum airframe as it descends through the atmosphere. It deliberately uses a very high angle of attack in order to maximize its drag forces so it can slow down as quickly as possible during the entry process. The Space Shuttle would then start gliding after it reaches subsonic speeds. During its descent towards the surface, the craft would ultimately stop by using a brake parachute on an airstrip. The shuttle was designed to be reused up to 100 times, but this never actually happened in practice. Wooden heat shields. In 1975, China launched an observation satellite into space. It weighed about 1,800 kilograms and was successfully launched 10 consecutive times over the next decade. The remarkable thing about this is that it used a wooden heat shield. The concept is that an ablative surface where the wood is burned into charcoal by the re-entry conditions and then dissipates into the atmosphere, allowing the next wooden surface to repeat the same process. They used white oak because it burns very slowly compared to other types of wood. Section 4, Future Reentry. One future application is a spinning heat shield. A team at the University of Manchester developed a prototype flexible heat shield that spins like a sycamore seed. Current designs require very large superstructures in order to support themselves against the re-entry conditions, or tanks to store gas for inflation in order to create the protection needed. This new development will be foldable like origami, therefore saving valuable space. The spinning design is supposed to redirect the flow of the atmosphere to create a larger heat boundary layer to resist the convective heating present in current atmospheric reentry processes. Transpiration cooling pumps a coolant to flow over a heated surface. This is already used in modern rocket engine nozzles to create a cool barrier of temperature. Researchers are planning to apply this same process to the heat shield too. The concept would be that the coolant would travel through newly invented and more porous materials that can still withstand the same high temperatures and pressures that current materials do. Here are a list of our references in case you would like to view them. And thank you for staying here for our presentation.